All right, today we're doing condensate and feed water. What is the purpose of the condensate system?
Cool the stain and recycle it, send it back up.
All right, condenser is to cool the steam. When we say, and that is a confusing little tricky thing. When we talk about the 4 parts of the steam cycle, and we say condensate as one of the 4 parts, we're talking about the actual condensing. But then when we say we're talking about turning steam into water. But then when we say the condensate system, we're kind of talking about from the Hotwell, which is where we've already got water from the condenser, up to the DA storage tank.
Preheat the water.
So we are preheating the water, and we are putting it in the DA storage tank, so they can which provides net positive suction head to the feed pumps. All right, what is net positive suction head?
It's like, basically like give it, like you don't want air bubbles in there, so you give it like more, I don't know how to explain this.
Now that wasn't terrible. that was an okay start.
So just give it more force as far as, so the boiler feed pumps have more, because the speed on them.
All right. So, first we're going to go with the engineering type explanation, the technically correct explanation. So, when the impeller sweeps by, then that, like a wing, creates a low pressure area in the fluid. And we know that when a fluid's energy gets less than a certain, or is too high for a certain amount of pressure, then it boils off. So when that impeller zips by, you get pockets of low pressure, which can cause it to boil effectively, and that is cavitation. There's these little bubbles that form and collapse, and then those bubbles chew up the impeller and do damage to your pump. Now, the way I actually conceive of it is I think of it as the pump sucking the water out faster than it can be pushed in, and that creates gaps. And that creates little pockets of like vacuum. And those little spots are where I see it. So there's 2 ways, but their definition is important because when the water's hotter, that's another thing that means you need more pressure because of their boiling explanation. But the key is to have enough pressure at the suction side of the pump that there's always water available for the impeller. So net means, you add up all the pluses and the minuses, right? And what's left over is the net. So you add up the pressure, and then you take away the vacuum, and then whatever, from the suction side, and whatever's left, if that's positive, then you don't get cavitation. Net positive suction head. Head's an engineering word for pressure. Suction head means it's on the suction side of the pump. Lots of words. I'm going to put that on the board because I put so much work into it. Net positive suction head. And it is measured in feet of water. It could be measured in any kind of pressure, but engineers like feet of water for that particular thing. I don't fully understand why. All right. So we've got a condenser. You've got steam that exhausts from a turbine. You've got a whole bunch of coils with circ water going through them, and that cools down the steam and collapses it into water, and we get water at the bottom. And coming out of that, you've got 3 strainers, which then goes to 3 pumps. And check valves. That was going the wrong way. And that goes up into the overhead and a common header. What is the first thing we run into? Polisher. What is the purpose of the polisher?
Clean all the ions that are bad in the water to good.
Outstanding. So, say, polisher removes ions. There is a bypass valve around the polisher. What makes that come open?
DP frost.
All right, so differential pressure of 50 pounds.
And temperature, right?
50 pounds DP across it, and what would make that happen is like if your polishers are getting gunk built up in them, then they start acting, instead of like an ion exchanger, like a physical strainer, getting fuckered up. And then that means it's harder for the water to get through, so that means there's more pressure on one side than the other. And what you're worried about is damaging like washing the beads out of the polisher and into the rest of the system, and your polisher's no good, and you're gonna clog up your feed pump strainers downstream. Temperature. What is the normal temperature on this header?
About 170.
Lower.
About 120.
I'll go with that. 120 is on the high side of normal. So if it gets up to 180, then this bypass valve goes open to take the heat off of the polishers to keep from melting all those resin beads into one big clump. Right now, is it open or shut?
Open.
Open. Kinda. Trick question. Open 50%. And that's because the system was designed to run with 2 out of 3 polishers in service, and we are only running with 1 polisher. We're back on 2 polishers again?
2 again tonight, I seen.
Well, then I'm wrong.
Normal operation.
Yeah.
Yes. So during normal operation, you only run with 1 polisher and you bypass the other. What's the advantage of doing that?
Take out all your ammonia.
All right. That is a major advantage, which I hadn't gotten to yet, so let's. So we are putting in aqueous ammonia, and this aqueous ammonia, what's the purpose of putting ammonia in the system?
pH control.
Up or down?
Up.
Raise the pH. So ammonia plus water creates NH4 plus ions and hydronium ions, and hydronium is a higher pH. So we put in aqueous ammonia, it breaks down and creates hydronium, which increases the pH, which if the pH is too low, it's bad for the pipes. If the pH is too high, it's bad for the pipes. We want to keep it between, it's a pretty tight range actually, like a 8.9 and a 9.4, something like that.
Good for us.
So then this goes through the whole system and into the steam, and then comes back into the Hotwell, and then the polishers clean it up, because that's what it does, is it removes ions. So the polishers take out OH negative, incorrect, take out the ammonia, NH4, and replace it with H plus, and the H plus and the OH minus get together and turn back into water. So, we're putting in ammonia to raise the pH, to protect the pipes. We have the polishers in service to remove ions because there's other ions, silica and iron ions in the water that are bad for the turbine blades and they're bad for the high temperature piping. So we got to make sure we keep cleaning those. But as a side effect, we clean up a lot of the ammonia, which means that we have to put more ammonia in, and you use 2 or 3 times as much when you have both polishers in service as opposed to when you're bypassing. I was not done with that bypass valve. All right, so right now it's shut and we're on 2 polishers, and that is because we have air in leakage in the condenser, and that makes weird things happen with chemistry. And so we have not been able to maintain our 95 percentile A+ ERPI standards on chemistry on 1 polisher. But there's other things that are nice about it. So we've kind of been going back and forth. This is the 2nd time in this 40-day run that we've gone back to 2 polishers. All right. The other reason this bypass valve is open is on a system start. When you have no pumps running, that initial water hammer, they don't want slamming the beads. So this valve will go open all the way when there's no pump running. All right. So we went through the polishers. What is the next piece of equipment we hit?
Gland seal steam condenser.
All right. Gland seal exhaust condenser. You got me screwed up there. What is gland seal exhaust? What seals are we talking about?
Seals in turbine.
All right. So you have a high pressure turbine and it has steam that wants to leak out into the space. You have a low pressure turbine and it has around the shaft, it's under vacuum and it wants to pull air into the system. And both of these things are bad. So the seal steam is at the transitions where you're casing for the turbine, where the shaft is penetrating at. It sprays steam, 4 pounds of steam, all the way around in a circle. And then on the atmosphere side, you've got this guy that is pulling vacuum off of it. And it's got a little blower system that is blowing out the roof to make sure it maintains its vacuum. And then you've got 120-degree water going through it. And then you've got steam on the other side. And then the water cools the steam and turns it into water. And the condensate heats up and the steam cools down. And then that has a loop seal. And then what?
Go back to
Miscellaneous drain tank?
Miscellaneous drain tank. So that goes to a tank. And then that tank has an automatic valve that looks at its level. And it says when the tank starts to get full, it opens up and it lets the condenser suck the water out. All right. I'm feeling I don't usually end up going that deep into the gland steam exhaust condenser. Coming out of the gland steam exhaust condenser, what's next?
Okay,
I got too many answers at once.
I said heater too.
That's wrong.
so
So
name 1B.
okay, that's before heater 2.
DLM control.
DA level control valves. All right.
Yeah, big book, I was thinking.
I don't know how we skip straight to heater 2, Josh.
I forgot about 1A and 1B.
All right, so you got 3 valves there next to each other. You've got these. You got 2 of them that are capable of maintaining full flow, full load on their own, and then you got one that is smaller for startup, because during startup, these guys trying to maintain 5% for a long time is bad for their seats and they wear out. So you start out on the little one until you get up to about 200 megawatts or so, and then it swaps. All right, I think we had all the rest of the components listed there. So we go from there to the drain cooler. We go from there to here's 1A and 1B. Go from there to heater 2. And there to heater 3. So you can tell I'm poor at planning because each heater gets smaller, and that's not how it works in real life. Lansing exhaust condenser is the smallest of them. And then that goes into the DA. All right. So heaters 1, 2, and 3. They're heating the water. How are they doing it?
Extraction.
All right, so they have extraction steam that they are scooping off and stealing from the turbine. So this is steam that's already gone through a whole bunch of turbine blades. It's already given up a lot of energy. It's already earned its fucking keep. And we are using it to preheat the water. Because the hotter the water is, when it gets to the drum, then the less coal we have to burn. So we are more efficient. Somebody better at math than me determined that this steam is more valuable preheating. It saves us more money by preheating the water than it does by making megawatts. See, there's also MOVs on the inlet and outlet of these guys, and there's bypass valves. And then there's another bypass around drain cooler 1A and 1B all at once. So 1A and 1B are a little bit different because they are physically in the neck of the condenser. The drain cooler is different. All these are U-tube and shell, where the water is inside tubes that goes down, goes up, comes out. Drain cooler is also the water is in tubes, but it doesn't make a U. It goes one way, and on the opposite side of the drain cooler, where the drain water is, it's also water. It's not steam, and it's flowing in the opposite direction. Single pass counterflow heater. So that heats the condensate, cools the drains, and then the drains make their way back to the Hotwell. DA level control valves are looking at the level in the DA storage tank. Just make that look around. There is flow meter right here upstream, the Lansing exhaust condenser. All right. Right here, a whole bunch of stuff happens. What taps off there?
First thing comes out, casing spray, but you might be looking for research, I don't know.
All right, no, I'm looking for all of it. You're right. Casing spray does physically tap off upstream of that. Casing spray. At low loads, casing spray valve comes open and it sprays on the inner shell of the turbine casing, and then drains down to the back into the hot well.
Go back to your CSG tank, recirculate back to your Hotwell.
All right. So minimum recirc, and then curtain spray, and then to high level dump. So if the level in the hot well starts going up, then this high level dump opens up to let water out of the system faster, to put it back into the CST. You got a recirc valve that goes back to the hot well. You have curtain sprays. When do we use curtain sprays?
Think we got a leak?
No. Startup is true. It's more. I got a more specific answer than that. When you're on the main steam bypass. So main steam bypass takes pressure off the main steam header and it puts it into the hot well, onto the circ water, and it collapses. And the curtain sprays kind of push it down to make sure it doesn't come back up into the turbine. Because you don't really have your good vacuum yet. You don't have steam pushing through the turbine to make sure it goes that direction. So you kind of have, you don't really see it that much anymore, but back in the day, stores would sometimes have an air curtain that would blow, and it, you know, it's just blowing all the time, and it's keeping the cold air in and the hot air out. It's kind of like that. It's like a water curtain that keeps the stuff going, keeps the steam going the direction you want it. What am I missing? There's some other cooling sprays that come off in here. And it cools the main steam bypass, and it cools the lead drains at the control valves, and it cools the cold reheat drain, and the hot reheat drains, which are hardly ever open. The main steam drains. There's a whole bunch of drains that go into the hot well, mainly during startup. And there's cooling sprays that cool all that water down so it doesn't fuck up your vacuum when it gets there. Let's jump way back to the beginning. In the overhead there, you got two lines right next to each other, about 3-inch lines tapping off. Right at that common header. One going in, one coming out. The one going in, before it goes up to the header, it comes down around shin level. Terry, what's that valve?
The CST condensate.
Outstanding. So the CST to condensate cross connects, the word we usually use. So CST condensate storage tank has pumps, and on an initial fill, before you start these pumps, you start the CST pumps and you line that up to the header, and then you'll be able to watch this pressure come up, and it'll come up really slow until it gets full up to these control valves. And then when it gets there, it'll start climbing pretty swiftly because it's no longer gravity. Now it's pump head. And then that, I want to say 110 pounds. That number might be off. What kind of pressure do you see when the condensate pump's running?
480,
Yeah, about
500, somewhere right in there.
480 to 550.
All right. So 480 is like a full load number, and the lower the load, the more these valves pinch off, and the higher that drives the pressure up at the pump discharge, and that's where you get those 500, 550 numbers. So you line up the CST cross connect, you fill it up. A good control room operator might want you to pinch back on the discharge valve at the condensate pumps to reduce the water hammer. You can also vent air bubbles out of the system at various drains and vents and places, and that will reduce the water hammer. Lots of times during startup, it's like all of a sudden things have been kind of slow for a couple of days, and then all of a sudden it's like, oh, we gotta go, because now it's funny, because time always matters, but it's not always operations' fault. Lots of times we're waiting on somebody else to do something, so this is the hurry up part of the hurry up and wait. All right, this other line that's tapping off. Anybody got any guesses where that's going?
3 inch.
Yep.
They got your ox steam temperation.
Ox steam temperation. Outstanding, Jackie. So just like I said, we had all these other things to cool off. This 3-inch header is going all the way up to the 17th floor, where we've got 3 supplies for your ox steam header: cold reheat, ox boiler, which you almost fucking never use, and the primary superheat. When you're coming off the primary superheat, that steam is 900 degrees, and that's not what we want. So we spray ox steam into it and de-superheat it. So superheating is when you take steam that's at saturation, you heat it up. De-superheating is when we cool it down. I think that might be the condensate system. What am I missing, Jackie?
The oxygen
Yep.
injection, sample.
All right. So right here where we put the ammonia in, we are also putting in oxygen, and we are taking a sample. And that sample line is shared. There's only one analyzer, and you can line it up either to the header or to one of the individual polishers. All right. So we inject oxygen. This is not a common power plant practice in America anyway. They say in Europe this caught on better. And we are, I think it's still true, are we still the newest coal burning power plant in America? Even though we're like 10 years old? Because coal is going out of fashion? So, you inject oxygen into the water, and you say, we don't want oxygen in the water. Oxygen causes rust. Okay, yeah, you're right. But there's a special kind of rust that they call a passivation layer. Passivation layer? All right. So the idea is that you get this certain hard layer that then acts to protect the inside of the pipes from real rust, from bad corrosion. And what they're really worried about is like a spot where the corrosion starts digging down and eating, more than they are the whole thing fucking shedding off. All right, well, I got a DA drawn already. So the DA, de-aerator, is meant to take all the air out of the system. And so you've got 4 valves up top that all go to one header, one pipe going out the roof that is letting steam out of the DA. The DA itself has a whole bunch of plates in it. And the plates have little holes in them. And the holes don't line up from one layer to another. So it has to take a tortuous path. So it takes time for it to get where it's going.
Can you see the message? Said you're about to be tired of it, locked out.
I am.
Yeah.
I hope not. If it is what it is. Alright, and then coming in the side of the DA, we have steam heaters 1, 2, 3. This is heater 4. So this is also extraction steam coming from the turbine, and it is blowing sideways across those plates, which is as the water drips down and the steam blows in, then it gives the non-dissolvable gases, non-condensable gases, that's the phrase, non-condensable gases a chance to go out the vent, along with steam. So having these vents open is wasteful. And during startup, we have them open because during startup, everything was just sitting around getting oxygen in it. And then as we cycle through the system, we get all the oxygen driven out, and then we can shut these vents, and then we can put the oxygen back in there, so we have the right amount of oxygen to get the right kind of pacifism in the layer. All right, we're going to call this one.